Galaxies with a small asymmetry in the RC of a few kilometers per second are well known. Larger RC asymmetries are less appreciated. The evidence that the cluster environment affects RC shape appears contradictory. These studies concentrated on the ionized RCs. The molecular hydrogen RC usually extends farther outward than the ionized hydrogen RCs. Therefore, the molecular hydrogen RCs are more sensitive to neighboring galaxies' effects. Because the observational data from each side of a galaxy RC are generally averaged, only highly asymmetric cases are recognized. The RC asymmetry appears to be the norm rather than the exception. These guys proposed the implied mass asymmetry is due to an imposed lopsided potential caused by galaxy interaction. RC asymmetry of early type galaxy falls by a factor of 2 between inner and outer regions. However, the problem is they can't quite get the math to work. However, no model has been presented that explains the data. The formation, evolution, and long-term maintenance of galactic kinematical asymmetry remains a mystery. Molecular hydrogen measuring equipment was improved in the 1990s. Such observations detected an abrupt change in the extreme outer region in many galaxies. This characteristic is ignored in current models. For example, some researchers consider this factor as a reason to exclude galaxies from the sample. We saw this in the rotation curve video, and there's the outer region as you see here. The STOE has three forces acting on it, as we saw in the rotation curve video. The first two terms were described in the RC video. This time we're going to take account of the last term, whereas that indicates absolute value. K is a constant vector, and the A0 is the acceleration caused by neighborhood galaxies. In the second approximation, we start with the first term, which is this, and then we add this term, which then turns out to be a residue between the data and the first approximation. The vectors are because the direction of the acceleration effect on the host galaxy depends on the relative direction. For example, a neighbor along a normal axis of the host galaxy has no effect on the RC. A neighbor in the plane of the host will have maximal effect. This direction dependence is captured in the K vector term. We saw this from the RC video, whereas that is the residue we're talking about, like that. I would note that if we want just one line, we take A equals 4.5, like was suggested in the RC video, and then we do the errors, and we see that the residue of some of these is going in the wrong direction. This makes it very difficult to explain the asymmetry. What is the measurement of asymmetry? Note the R major factor in this term. The asymmetry then is the maximum difference in rotation velocity in the outer RC from one side along the R major to the other side of the galaxy. That is to say, R major is kept constant for the measurement. This differs from other researchers' definitions. Other researchers consider the difference in radius at a constant rotational velocity to be the measure of asymmetry. This doesn't fit easily into equations of force and rotation velocity. So this then is the result for the galaxies that we use in our sample. Again, we have the error bars put on the 16 select galaxies that we had before. So the RC parameter, rotation velocity for instance, or some radius, is equal to this kind of an equation where again A and B are integers. In looking at these galaxies, we end up with generally about a 3% uncertainty in the various parameters. This is vastly better than we had before. The neighbor galaxies cause much of the error in the first approximation. And when other people do the measurements, the neighbor galaxies would also be better for them also. Because the neighbor galaxies cause the asymmetry in the host galaxy, the long-term maintenance of the asymmetry is easily accounted, unlike other models. The STOE does not use a mass-to-light ratio to fit RCs. The calculations imply the effective mass-to-light ratio varies among galaxies, as has been observed. The use of the M term, derived from the Tully-Fisher relation, and the degree of correlation achieved herein suggests the mass term is totally determined by baryonic matter. The gradient of the scalar potential serves the same role in the equations as dark matter. The subtraction of the L term from the mass term suggests a much larger spiral galaxy baryonic mass than traditional Newtonian mechanics would calculate. Therefore, the scalar field causes Newtonian kinematic measurements to considerably underestimate the mass in a galaxy. The difference between the STOE and other RC models of the missing mass problem is that the added mass follows the luminance mass in the equations. Therefore, the added mass is baryonic rather than dark matter, or rather than a changing gravitational constant, or rather than a changing acceleration, or other form of fifth force. The missing mass is non-luminous baryonic matter. This paper describes the physics here involved,